Let us begin by recalling that Lebesgue outer measure satisfies certain nice properties. I won't list the properties one by one. However, let me mention the following. Let us recall that the Lebesgue outer measure M star is a function M star defined on power set of R to 0 infinity. So M star is well defined for all subset of R. Further, M star enjoys certain nice properties of length for an interval. Okay. So the good news is that M star satisfies several nice properties such as monotonicity, translation invariance, etc. of length for an interval. However, the message from the last lecture is the following. Though M star has many nice properties, M star is not a perfect way of measuring subsets of R. In other words, there is a bad news. The bad news is that M star is not additive. That is, there exists a pair of disjoint sets A1 and A2 in R such that M star of the whole A1 union A2 is not equal to M star of the parts and summing it. M star of A1 plus M star of A2. And we have seen that this is equivalent to or equivalently there exists a countable family of disjoint sets An. N varies over set of natural numbers such that M star of union is not equal to summation of M star of An. By invoking axiom of choice, we could get such a countable family of disjoint sets. That is, M star is not countably additive. This is what we have observed in the last lecture. Yes or no?
Yes, sir.
Yes.
Now, because of this disappointing result about M star, it is natural to suspect that the way in which you have defined M star may be the reason for such an unpleasant thing. Yes or no? That is, maybe instead of Lebesgue countermeasure, if you use some other definition or some other measure, then probably you may get all the properties that you are looking for. That is one way to, immediately after this result, that's what one suspects. Okay. So let me put it as a question. The question is, can this unpleasant issue be settled by using some other notion for measuring subsets of R? Not the Lebesgue countermeasure. Do you understand the question? There is some issue with the Lebesgue countermeasure. You have seen. Lebesgue countermeasure does not satisfy the intuitive property that we want. Namely, measure of a whole is equal to sum of the measures of its disjoint parts. That is not true. Therefore, we naturally will suspect that by modifying the definition of M star somehow, we can come up with a new measure which satisfy all the properties that we are looking for. Is that clear?
Yes, sir.
However, we have the following theorem, okay, towards the answer for this question. Towards the answer, we have the following theorem. If my memory serves me, that's where we stopped our last lecture. The theorem is as follows. There does not exist a function mu satisfying the following properties. For future reference, these properties I would name as desirable properties. One, mu is defined from 2 power r into extended non-negative real number 0 infinity included. 2. Mu of I coincides with length of I for all open set I. 3. Mu is countably additive. That is, for a countable disjoint, when I say disjoint, I mean pairwise disjoint. Family An, n in n, of subsets of real number system, mu of union An is equal to summation mu of An, and 4. Mu of the translated set A plus x or x plus A is equal to mu of A for all A subset of R and for all point x in R. Okay. So the theorem says that however hard you try, you cannot come up with a function satisfying all the 4 conditions. This is where we stopped our last lecture. Am I right?
Yes.
Yes.
So let us prove this theorem. Proof. What is the line of attack? The line of attack is as follows. Suppose mu satisfies these 4 desirable properties. Then, using these 4 properties, we will prove that mu satisfies all the properties of the Lebesgue countermeasure which we used in proving the unpleasant thing about M star, the Lebesgue countermeasure. Okay, that means we will prove that mu satisfy all the properties of Lebesgue countermeasure M star that we used in those 2 theorems. I think we named it as theorem T1 and theorem T2. Am I right?
Yes, sir.
We need to refer to that theorem. So please tell me, is it correct? T1 and T2 were the 2 theorems.
Yes, sir.
Okay. So what we will do is, suppose there exists a function mu. For a moment we are assuming this, that satisfies all the 4 properties listed in the theorem. What we will do is the following. We shall prove that mu has all the properties of the Lebesgue countermeasure that we used, all the properties of Lebesgue countermeasure that we used in proving theorem T1. But instead of theorem T1, actually we proved theorem T2. bar theorem T2. So let us do one by one. First, we know that Lebesgue countermeasure of null set is 0. Whether mu, which is an arbitrary function satisfying all these four properties, will also have that property, namely mu of null set is equal to 0. Mu of null set. What do you think? Can you say mu of null set equal to 0 from the four properties given to you?
Yes, sir.
Look at the second property. Mu of I is equal to length of I. Oh, not for the open set, okay? Open interval is enough. Of course, we can do for open set once you have for open interval, but I will write for open interval. Once you have for open interval, you can, yeah, but it's better to write for an interval, for all open interval. Yeah. So use that second property, mu of I equal to L of I. A null set can be treated as an open interval. Okay. Therefore, mu of null set equal to 0. Null set can be treated as an open interval. So using 2, we have this. Okay. Now I want to see whether mu has monotonicity property of the Lebesgue countermeasure. Okay. Let A subset of B both are in R. I want to see whether mu of A will be less than or equal to mu of B. I don't know what is mu, but I know only that mu satisfy those four properties. Okay. So can I write A or B as A union the difference B minus A? This is just set theory. Okay. Note that. Now let us apply the third property, that mu is countably additive. From third property of mu listed in the theorem, statement of the theorem, mu of B is equal to mu of A union B minus A, which is equal to mu of A plus mu of B minus A. Both these are non-negative, and therefore the sum will be greater than or equal to mu of A. Okay. Or mu of A is less than or equal to mu of B. Okay. Now we know that Lebesgue countermeasure of any interval is its length. Let us see whether the mu also satisfy that. Mu of I equal to L of I is given only for open intervals. Okay. So let us see. Consider closed interval AB, A comma B in R. Note that for now I wanted to use open intervals and then get the measure of AB. For any epsilon greater than 0, open interval AB is contained in closed interval AB is contained in open interval A minus epsilon B plus epsilon. Now using the monotonicity property of mu, which just now we proved, therefore mu of open interval AB is less than or equal to mu of closed interval AB is less than or equal to mu of this interval A minus epsilon B plus epsilon. And this is B minus A. B minus A is less than or equal to mu of closed interval AB is less than or equal to B minus A minus 2 epsilon. But epsilon is arbitrary. Since epsilon greater than 0 is arbitrary, what can you say? Mu
B
of
minus A plus 2. Sir, there should be B minus A plus 2.
plus 2 epsilon. Yeah,
Yes, sir.
that's okay. So what can you say about this? Mu of AB is equal to B minus A. So mu of a closed bounded interval AB is equal to length. Now, once you have it for closed bounded interval, now you can prove for any interval. Okay, any interval, whether open or closed or semi-open or semi-closed, finite or infinite, doesn't matter. Okay. Now we can see that I will not do that is exactly how we did for M star. We can see that mu of I is equal to length of I for all intervals I. Now there is no specification on I, open, closed, finite, infinite, anything. Okay. Now let me observe another property that M star has, namely countable subadditivity. What is given to you is mu is countably additive. But keep in mind that countable additiveness is something to do with disjoint family, whereas countable subadditivity is something to do with arbitrary collection. Okay, so let sequence n belong to n, be a countable collection of, I don't assume disjoint, countable collection of subsets of R. I have to see whether mu is countably subadditive. Okay. What I can use is countable additive. But once I have to use countable additive, I have to have disjointness. Okay. So how to do that? Then how to make a disjoint set? Then A1, as you know, A2 minus A1, pure set theory. A3 minus A1 union A2 and so on, okay, is a disjoint family. It's a disjoint family of subsets of R. Okay. Further, if you take the union of this set, you will get union of AN, whose union is union AN, n belong to n. Okay. Therefore, mu of, which I don't know concretely what is mu, but I know only mu satisfies certain properties. Mu of union AN is same as mu of A1 union A2 minus A1 union A3 minus A1 union A2 union so on. Okay. And now using the third property of mu, this is equal to mu of A1 plus mu of A2 minus A1 plus mu of A3 minus A1 union A2 plus so on. Please bear in mind that A2 minus A1 is A2 intersection something. In fact, A1 complement. Therefore, A2 minus A1 is a subset of A2. Therefore, you can use monotonicity and say that second term is less than or equal to mu of A2. Are you with me?
Yes, sir.
Yes, sir.
Now look at the third term. A3 minus A1 union A2. That is the set involved in the third term. And A3 minus A1 union A2 will be subset of A3. Therefore, mu of A3 minus A1 union A2 will be less than or equal to mu of A3 and so on, which is less than or equal to mu of AI, summation or AN, doesn't matter. It is dummy variable n belonging to n. Okay. That means that is mu is countably subadditive. Now, if needed, you look back at the proof of theorem T1 or theorem T2. You will see that these are the properties of M star we have used there in the proof. Okay. Thus, we have shown that mu has all the properties of the Lebesgue countermeasure M star, Lebesgue countermeasure M star, that we have used, in the proof of theorem T1 or theorem T2. Now what you do? You repeat that proof of theorem T1 and theorem T2, and wherever you see M star, replace it with mu, because mu satisfy all the properties of mu star we used there. You just repeat that proof by cutting M star there and pasting mu everywhere. Okay, repeating the proof of theorem T1 bar theorem T2 by replacing M star direct. Wherever you see M star there, by replacing M star direct by mu, we get. So what will you get? Tell me. If you repeat that proof, what will be the final output?
Not countable.
I don't hear.
Mu is not additive.
In other words, you just go for the theorem T1. There exists A1 and A2 such that mu of A1 union A2 not equal to mu of A1 plus mu of A2. We get two sets A1 comma A2 that are disjoint, such that mu of A1 union A2, this is actually theorem T1, not equal to mu of A1 plus mu of A2. So, do you get a contradiction now?
Yes, sir. Third point.
Yes, sir.
It contradicts the third one, which is a contradiction. Because mu satisfy 4 properties, out of which 3 tells that it is countably additive. What is the source of this contradiction? Your wrong assumption that there exists a function mu that satisfy all the 4 properties. Okay, so this proves the theorem. Thus, the theorem. So outer measure doesn't have one property that we are expecting. So it is natural to think that the culprit is outer measure. You change the definition of outer measure properly, get something else, so that that something else will satisfy all the properties. That's what our expectations will be initially. But the theorem now tells you that however hard you try, you cannot come up with a function. Forget about outer measure, Lebesgue outer measure. You try to construct your own function satisfying all the four conditions. You will never succeed. That's what the theorem says. Yes or no?
Yes, sir.
So the message is the following. So what is the message of the last theorem? The theorem says that if you want to extend the notion of length and you want to measure more general subsets of R, that is our goal. In that goal, we should give up one of these four desirable properties. You cannot have all the four at a time. Okay, so you should have some trade-off. Among these four, which one we should select? All the four definitely you cannot select. Okay, so let me first write that. The message of the previous theorem is the following. The last result shows that let me write like this, in our goal of extending the notion of length of an interval to measure of more general subsets, we must give up at least one of the, we should drop one of the four desirable properties listed in the theorem. This is the message. So far, so good.
Yes, sir.
Yes, sir.
We should drop one of, we should relax. We cannot have all the four conditions. Okay. Now you just look at one by one. What you are looking for is some measure consistent with the length. Therefore, second condition cannot be dropped. That is for sure. And you have seen in the initial lectures that a measure intuitively should satisfy the property that the measure of whole is equal to sum of its disjoint parts, and also it should satisfy the principle of exhaustion, and therefore I need countable additivity for any measure, so I cannot drop third one. Okay, so now the trade-off is between 1 and 4. Which one I should avoid? Okay, but since you are looking for something which extends the length, and length in R is translation invariant, it is natural to keep that property 4 and think of some measure which is also translation invariant. So we will not try to drop 4. So only thing that we will drop is property 1. Okay. Let me write that also so that in later you can understand what is going on. We cannot give up. We cannot give up properties 2. I think 2 is length property, and 3 is countable additivity. Properties 2 and 3. Okay. Now between 1 and 4 you have a trade-off. For a measure consistent with length, we shall keep property 4. Okay. So what is the climax? What's the climax of the previous theorem then? Tell me.
We shouldn't be too ambitious.
And we are forced to relax the requirement that measure should be defined on all subsets of R. Okay. So that's the climax. Let me write as it is. We are forced, and this is the starting point of what we are going to do next. We are forced to relax the requirement that measure, any measure, but we already have outer measure, so let us try with outer measure itself. The requirement that measure is defined on 2 power R. So instead of working with the power set of R, we shall work with a suitable family of subsets of R, such that in this family, if you take disjoint union, measure of outer measure of disjoint union is equal to sum of the outer measure of the individual. Okay, that we want to maintain. Countable additivity we want to maintain, but we cannot maintain on entire 2 power R. So wherever you have problem, those sets we have to drop from 2 power R. Those sets we should throw it from consideration. Okay. Therefore, we shall work with a suitable family of subsets of R. Suitable family I will put as M. Okay. Suitable family M of subsets of R such that the outer measure, already we have outer measure, so let us try with outer measure itself. The outer measure of countable family of disjoint sets in M, that family M is the sum of outer measures of the individual. So from 2 power R, we should confine to some suitable subsets M. And if I take An, n belong to n, in M, An's disjoint, then I should have mu star of union An is equal to summation mu star of A. That is our next target. Is that clear?
Yes, sir.
So now, how do you come from 2 power r to m? What sets we have to throw out? What is suitable m? And so on. There are several questions. Of course, all these questions are related. What is that suitable m that one should work with? Don't say sigma algebra, that is okay. But what sigma algebra that we have to work with? Okay. And this leads to the notion of measurability. This leads to the notion of we will define something called measurability or measurable subset. And that notion will finally tell you what is this m that we are looking for, or measurable subset. Is path ahead clear? What we are going to do? We are going to look for a suitable family M such that on this family, the outer measure satisfy countable additivity so that we are okay. So we should not be too ambitious to consider entire power set, but if you relax, if you confine suitably, everything works fine. How to reduce? Which m I should take? That's the question that we have next. Is that okay?
Yes, sir.
Now, there is a standard way in which people define this notion, measurability, or when will you call a set is measurable, and then develop based on that definition, and then slowly tell what is this m we are looking for. That is the approach you will see in almost all standard books. But I will not do that because I feel that, of course, I can straight away give this is the definition of measurable sets. But if I do that, then the motivation behind that definition, why we are defining like that, the intuition behind such a definition will not be clear. That is one reason why I don't want to directly give the definition of measurability. Second reason is that, see, our aim is to come up with a suitable m. We cannot work with 2 power r and we have to come with m. How this definition of measurability will help us to achieve it, come up with a suitable m, will not be clear if I directly give you the definition. And third reason why I don't want to directly give the definition is Lebesgue did not do in that way. The original approach of Lebesgue is slightly different. So I wanted to follow those lines and motivate, give some intuition behind the definition, and finally give this is the definition for measurability. Is that clear? Is it sound good?
Yes, sir.
So with one line, I can give a set is called measurable if the following condition is satisfied. But the question is, why one should make such a definition? How that will help to achieve our goal? Okay. Those things will not be very clear. The intuition behind such a definition will not be clear. So I will not do that. Okay. So the approach that I am going to take is also available in a very few books and very few articles. But most of the standard books at this juncture, what it does is it starts with a definition. A set is said to be measurable if the following condition is satisfied. Okay, why should one call it as measurable? What is the idea behind it? How it settles our question that from 2 power r, we should go to some other family. Those things will not be clear. Okay. So here, let me slightly take a different approach than conventional textbook like D. Bara or Royden. These are the two books that I have given you as a reference. Okay. Or any other book for that matter. Only very few articles and very few books does in the way that we are going to do. Okay. So let me write that also. We shall approach measurability slightly differently as follows. There are multiple reasons of doing this. You will see what are all those reasons. Okay. Let us start by recalling what was the basic idea of outer measure. Okay. Recall, not the definition. Okay. Recall the basic idea of Lebesgue outer measure. Of course, I know by this time you all know the definition, but I would suggest you to recall the way in which it was developed. I know how to measure open intervals. Just take length of that interval. Okay. Let me quickly write how we developed outer measure. If I is an open interval, m star of I you can take as L of I. Okay. So now I know how to measure open intervals. So the collection of sets under consideration is all open intervals. Now, suppose a set is disjoint union of open intervals. Let A subset of union In, In's disjoint. Then I will define not subset, sorry, equal to. Suppose A is countable union of disjoint sets, intervals, disjoint intervals. Maybe you can avoid open here, doesn't matter. Or you can keep it also. Yes, it is better to keep. Disjoint open intervals itself. Okay. Then I can define m star of A is equal to summation n L of I. So from intervals, I went up to disjoint union of intervals. Next, let A is equal to union n Jn, where Jn's are open intervals. I don't know whether it is disjoint or not. Then we can write A is equal to union n In, In's disjoint intervals. And we can define m star of A is equal to summation n In. So now the family of sets under consideration is enlarged. You can also take any union of open intervals. Next comes Lindelof theorem. You know that every open set in R is a countable union of disjoint open interval. G subset of R, G open, G a open set implies G is equal to union In's disjoint open intervals. So now I can define measure for open sets and define m star of G is equal to summation n length of In. So now open sets are like standard objects whose measure I can define. So from intervals, we went all the way up to open sets. Okay. Next, let A be any subset of R. Then there exists an open set G containing A such that A is contained in G. Any set given, you can enclose inside a open set. Is that true? We are in R.
Yes, sir.
At least R, whole R you can take, for instance, trivially. Okay. So given any set, I can always find an open set larger than it. And I can find an overestimate for measure of A, which is I will take measure of G as an overestimate for measure of A. Okay. M star of G is an overestimate for M star of A. Now, what we have to do? The best overestimate possible. Okay. So we define M star of G as, M star of A as A is the set we want to measure. G is an open set, which is like some standard object which we know how to measure. M star of A is equal to M star of G you find and then take infimum where G contains a G open. Okay. This is the basic idea behind Lebesgue outer measure. Starting from interval, you can go up to open set. Now, any set, you can estimate its measure using open set and make that overestimate better and better by taking greatest lower bound. Okay. Is that clear? This is done already, but I am just reminding you. Is that okay?
Yes, sir.
And
Yes,
also, I have told you that there is no need to work with open sets because any open set is union of open intervals. That is why in the definition we took it as infimum of summation L of In and so on. Okay, so that I am not writing anyway. So this is the way in which we developed the Lebesgue outer measure. So naturally, you can ask one question. Why you are always trying to do overestimate, that is you are approximating from outside. Given an A, you are finding a G larger than it and you are making that G smaller and smaller, infimum. So this is approach from outside. That is why the name came outer measure or external measure. So you may ask, why not from inside? Okay, why don't you do from inside? One difficulty that you will face is the following. When you do estimate from inside, you cannot use open intervals because given a set, I don't know whether there exists an open interval inside it. Given a set, I can always find an open set or in fact open interval for that matter larger than it, R itself. But given a subset of R, I don't know whether I can find an open interval inside it. Do you agree?
Yes, sir.
yes, sir.
For instance, you take Q, set of rational. You don't have any open interval inside Q. Okay, so that is one difficulty. Okay. So let me first note that. First note that given A subset of R, there may not exist an open interval contained in A. So approaching a set from inside using open intervals or open sets is at least not approachable. You can't do that as such. Okay. So let me also give an example. For instance, take A equal to Q. That doesn't mean that you cannot do at all. So there is some way to do. Slightly you have to modify. Okay. Let me take and
Sir, empty set is inside Q and it is open.
okay. So you've got M star of null set, right? So what is the other thing that you can do? And it has measure 0.
Yes, sir.
Yes.
Then the next step. So you want a non-trivial thing, right?
Yes, sir. Yes.
Yeah. So this will not help you. You are right. Null set can be treated as an open set, and in fact, it is an open interval. Okay. So I will polish my statement. There may not exist a non-trivial. I will write. So that may not be a suitable approach. If you want to find underestimates and make that underestimate better and better, looking for open intervals may not be a good approach. That is the message from this. Okay. But what is the way out? How to do it? Let me consider the following. Consider a closed bounded interval. I is equal to AB. I will not work with R for the time being. You will see why. Now my world is closed bounded interval AB. And let A subset of I. Okay. And let A subset of I. I want to approach this A from inside. I want to approach this A from inside. Though everything happens in real line, I will put circles that will be more easy to do, and also you can get a visualization. So this is, we are in AB. This is our world. It is bounded. Okay. Inside that you have A. I want to measure A from approaching from inside. Okay. So do you agree? At least intuitively, is it clear that approaching A from inside is same in some way as approaching its complement from outside?
Yes, sir.
Yes, sir.
If you want to approach A within, it is same as approaching its complement from outside the complement. Right?
Yes, sir.
Now define inner measure of A, not outer measure of A, inner measure of A as inner measure. So I am going to approach A from inside. Okay. I will not use open sets and then take Suprema or whatever it is. But what I will do is this. I will attack A from inside by attacking A complement from outside. For A complement, I know outer measure. Outer measure I can define for any set. No. So I know M star, sorry, superscript star of A complement. I know this. Can you guess a natural definition for inner measure of A using outer measure of A complement? You guess. Tell me what can be. You are in the world AB, and do you know measure of AB?
Yes, sir. B minus C.
So total measure is B minus A, and you
Yes,
want to approach A from inside. Now tell me what can be the possible definition of inner measure of A?
Outer measure of whole minus outer measure of A complement.
What is outer measure of whole?
Minus
B
A.
minus.
B minus C.
This is what Lebesgue did. Okay. So he defined inner measure of a set via outer measure of its complement. Now at this juncture, you should also see why I use bounded interval AB. Why I did not take the whole interval R. Is it clear?
That will become infinity.
And then I cannot define it, no?
Yes, sir.
So at least for sets inside a bounded interval, I know what is inner measure now. How do you do? Intuition. Don't worry. This is, we are not going to write rigorous mathematical. That is coming. This is just to motivate you what is happening. The inner measure approaching a set from inside is equivalent to approaching its complement from outside. So you define inner measure of a set as the universe. What is the measure? That is B minus A. That's why we are taking our universe to be bounded minus the outer measure of the complement. Okay, so this is how we define inner measure. Is that okay? This is just intuition.
Yes, sir.
So
Yes,
now I can define inner measure only for bounded sets. Then only I can say that a set will be contained in some bounded interval. Otherwise, I cannot do that. So for all bounded set, I have defined inner measure. Do you agree?
yes, sir.
Now,
Yes.
one way you can do how to, if you ask how to inner measure other sets, not bounded set, there are various ways. One is to do that you say that no, you find portion of that set in each bounded interval, and then use the inner measure of that portion and so on. Okay, but that's not what we are going to do. Let us stick to bounded set. Once your set is inside AB, I know what is inner measure. Okay. Now, if everything is fine, your expectation is the following, or should be the following. Whether you approach a set from inside or whether you approach a set from outside, the measurement should be the same in the ideal case. Yes or no?
Yes, sir.
Yes.
Yes,
That
sir.
means we expect that inner measure of a set and outer measure of a set. Now, set I mean only sets which are inside closed bounded interval AB should be the same. If your measuring process is ideal, we expect that inner measure and outer measure should coincide. Yes or no?
Yes, sir.
But that may not happen always. Okay. So what Lebesgue did is he defined a set to be measurable if inner measure is equal to outer measure. Okay. That may not happen. That ideally it should happen. Whether you approach from inside or approach from outside, the measure of the object should remain the same. But ideally it may not happen. So there is a question whether you will go for inner measure or whether you will go for outer measure for a set. Instead of answering that question, what Lebesgue did was he declared a set to be measurable if its inner measure is equal to outer measure. Okay, I will write that. Before that, this should remind you that Lebesgue has copied Raymond's idea.
Yes, sir.
Yes, sir.
Yes,
Yes.
sir.
what was Raymond's idea of integration? Upper Riemann integral. What upper Riemann integral is? Instead of
Point
measuring the area, he overestimated using rectangles.
Yes,
Right?
sir. Yes.
That is upper Riemann integral. Underestimated with the help of rectangle, that is lower Riemann integral. But unfortunately, upper Riemann integral and lower Riemann integral may not coincide. So a natural question is, given an integral, which one you will select, whether you will select upper Riemann integral or lower Riemann integral. And how he tackled that is, you consider only those functions whose upper integral coincides with the lower integral and call them as Riemann integrable and work only with those types of integrals. Okay, same approach. Instead of measuring area, now he is measuring any sets. That's the only thing. Okay, so he was inspired by Riemann's idea. Okay, now let me write it. We define a subset of I to be measurable if this is how Lebesgue defined measurability. Okay, measurable if M star A is equal to M superstar A, superscript star A. Okay, that is inner measure coincides with outer measure. So far, so good.
Yes, sir.
Yes.
And we define A to be Lebesgue measurable. Okay, this is Lebesgue measurable. But you should keep in mind, now for the time being, Lebesgue measurability is only for sets complete
Bounded sets.
inside a closed bounded interval. Okay, slowly we will remove that. So far the progress is, so why this approach I have given is also this will remind you that what is inner measure. There is something called inner measure. Okay, so approaching a set from inside is treated as approaching its complement from outside, and then we define inner measure in terms of outer measure of the complement. And in the ideal situation, we expect that inner measure and outer measure coincides. Whether you overestimate and make the overestimate better and better, or you underestimate and make the underestimate better and better, doesn't matter. Okay. If I remember, I don't know which professor, probably Vittal Rao, compares this with, suppose you want to measure 1 kg of sugar. You can put lot of sugar in balance and you can keep on removing until it becomes 1. Or you can put a smaller amount of sugar and keep on adding until it becomes 1 kg. You can either overestimate or you can underestimate. Are you getting me?
Yes, sir.
Yes.
If your measuring balance is too good, whether you do by putting lot of sugar and then removing it, or you are first putting small amount of sugar and go on adding, does not matter. Finally, you will get 1 kg of sugar. You can measure it. Okay, that is ideal situation. But in sets, it may not happen. So we are not worried about those sets in which it does not happen. We are worried only about the sets in which outer measure is equal to inner measure. And we call it as measurable. Now, we want to look this measurability in a slightly different way. Okay? Though the measurability comes like this, one thing is that it is defined only for bounded sets. And second thing is that it involves the idea of inner measure. I wanted to view measurability which in such a manner that it involves only the concept of outer measure. No inner measure is coming into picture. Okay, that's the next step I want to do. Let us begin like this. Consider A and E, both subsets of AB. Why I am taking inside AB? Because then only I can talk about measurability, at least now. Okay, now I can write A as A intersection AB. Do you agree?
Yes, sir.
Now I can write this as, because everything is inside AB, my universe is now AB. Okay, ambient space is AB. This E union E complement. Do you agree? Complement, when I say, it is with respect to the universal self, and universal set now is AB. And this will be A intersection E union A intersection E complement. Yes or no?
Yes, sir.
No.
Yes, sir.
All I know is that Lebesgue outer measure is countably additive. Sorry, countably subadditive. I don't know about additivity. Okay, since M star is countably subadditive, M star of A is equal to M star of A intersection E union A intersection E complement. And this is less than or equal to M star of A intersection E plus M star of A intersection E complement. So the total measure of A will be less than or equal to outer measure of A in E, the part of A in E plus outer measure of part of A in its complement. And this is true for all A and E inside AB. Okay. Thus, let me write once again. M star of A is less than or equal to M star of A intersection E plus M star of A intersection E complement. Okay. This is what we have. And this is true for any set A and B, A and E. Okay. Now, let us view this as follows. You have a set A. Okay. And you have a knife or a cutter or a slicer. That is E. I will put it as a square. You are trying to cut A with the help of E. You are slicing A with the help of E. Okay. Then A will be cut into two pieces. One is A intersection E and the other is A intersection E complement. Everything happens inside AB. Okay. And now I can measure A intersection E and I can measure A intersection E complement. And I can add, I am not getting M star A. I am only getting M star A less than or equal to M star of A intersection E plus M star of A intersection E complement. Are you with me?
Yes, sir.
Yes, sir.
This diagram you please keep in mind. A is like some set and E is like a slicer. You are cutting A with the help of the slicer E into two pieces and you are trying to measure A. But measure of A is now measure of A, part of A in E and measure of part of A in E complement. But if you find measure of this part and add, I am not getting M star A, but only there is something like a wastage. There is some wastage in this cutting process. Okay. Now the question that we want to ask is, what is perfect slicer? What is a good slicer? Okay. A good slicer E would be whatever set A is given, no, I want m star of A to be equal to outer measure of A in the part of E plus outer measure of A in the part of E complement. That's what I want. So let us ask the following question. For what subset E in R we have m star of A is equal to m star of A intersection E plus m star of A intersection E complement for all A subset of R. Whatever object I am giving, A I am changing. With this E, you should be able to cut it into two pieces. And if you add the measure of the pieces, I should get the measure of the original. Such a set E, I can call as a good enough slicer or a good enough knife. Are you with me?
Yes, sir.
No. So we are investigating what set E, what type of slicer I should take so that any set I can cut into pieces with this property being satisfied. So I am looking for E satisfying this condition for all A. Okay, so this is the question I want to answer. Let us see. Suppose this equality holds. Suppose E subset of R be such that I can cut any set with the help of E. And I can measure the whole as measure of part of it in E plus part of it in E complement. Suppose I can do this. And this is true for every A. Now it is not R, okay? My word is
Closed AB.
AB. So I should not say R. So there is a mistake here. Because finally I wanted to use this inner measure, outer measure, etc. Okay, so for every A in AB. And similarly, this is not R, this is in AB. As I told you, our universe is now closed bounded interval AB. So everything happens within AB. Suppose E subset of AB, sorry for that. Suppose E subset of AB is such that this happens for every A subset of AB. Okay, since it is true for every A subset of AB, in particular it is true for I is equal to AB. You know, in particular, for I is equal to AB, we have m star of A is equal to m star of A intersection I plus m star of A intersection I comp. No. I'm making a mistake. You have to tell me what. This is true for any A.
A, we have to
I am
write.
replacing A with I. Okay, so that is the mistake that I made. So I am. This is true for every A, in particular for I. M star of I is equal to m star of A is I intersection E, and then m star of I intersection E complement. Okay. And what is m star of I? B minus A? B minus A equal to, what is I intersection E? Remember, everything happens inside I. Okay.
E.
So this is m star of E. M star of E. Plus, and what is this?
M star of E complement.
E complement, when you say it is complement with respect to the universal set I. Therefore, this is again m star of E complement. Right? That is B minus A, everything is finite. So I can take this to other side. Everything happens inside AB. M star of E complement is equal to M star of E. Now can you see what is left hand side?
It is a
Inner
inner
measure.
measure.
Inner measure. So this is inner measure of E is equal to outer measure of E. Okay. And that implies E is, that was our definition, is measurable. Yes or no?
Yes, sir.
That means
Yes, sir.
if this, let me call it as star 1. Okay. Or E1. If E1 happens for every A, then that E should be a measurable set. What we are searching for is a good slicer. Okay, good slicer. Good slicer in the sense, whichever A I am giving you, you can cut that A with this slicer into 2 pieces and you can get the measure of the whole is equal to sum of the 2 parts. Part in E and part in E complement. Such a slicer I will call as good slicer. And this tells you that if a slicer is good, the slicer is measurable. Okay, good slicers are measurable. That's what you got. Is that okay?
Yes, sir.
Now I will go the converse. Suppose E is measurable. And I will prove that it is going to be a good slicer. That means E1 will satisfy. E1 will satisfy. Equation 1. Okay. So let me first write it. Thus equation E1 is satisfied implies the set E is measurable. I am going to prove that the converse is also true. Conversely, suppose E is measurable. Suppose E is measurable. I am going to prove that these measurable sets are good knife, good slicer. It can slice any set into 2 pieces and measure of the 2 pieces. If I add, I will get measure of the whole set. Okay, that's what I am going to prove. So let us start with any A. Let A subset of I equal to AB. This is our universe. Okay. What I want to prove? I want to prove equation E1. So I want to prove M star of A is equal to something. But what is M star A? Basically is an infimum. Yes or no?
Yes, sir.
Infimum means it is greatest lower bound. Therefore, if you slightly increase it, that will not become a lower bound. Anything greater than it is not a lower bound. Okay. Given any epsilon greater than 0, there exists in, this is from infimum definition, okay, in such that A is contained in union n in and summation length of in is less than or equal to m star of A plus epsilon. M star of A plus epsilon is not a upper bound, lower bound. Therefore, there exists something lesser than it. Is it okay?
Yes, Yes, sir. sir.
Yes,
Just
sir.
apply definition of infimum. Okay. Now, A is contained in union n in. That implies somehow I want to prove the equation E1. Okay. A intersection E is contained in union n in intersection E. And that will imply, these are set theoretic. Let me be quick here. A intersection E, let me copy from my note. Union n in intersection E. Okay. Similarly, Similarly, A intersection E complement will be contained in union and IN intersection E complement. Okay. So this is 2 and this is 3. Now, please keep our target. Target is to prove equation E1. Now let me look at M star of A intersection E. Since look at 2, A intersection in E is contained in this. Therefore, M star of A intersection E is less than or equal to M star of union N IN intersection E by monotonicity, by 2 and monotonicity. Is it okay?
Yes, sir.
Now M star is countably subadditive. So this is less than or equal to summation N M star of IN intersection E. Agree?
Yes, sir.
You
Yes,
have
sir.
to give me
Yes.
5 minutes more today. Now, this is M. Similarly, M star of A intersection E complement will be less than or equal to summation N M star of IN intersection E complement. This is again similarly same. Apply monotonicity and that containment. So now let me add. Therefore, M star of A intersection E plus M star of A intersection E complement will be less than or equal to summation N M star of IN intersection E plus summation N M star of IN intersection E complement. Okay. That is equal to summation N M star of IN intersection E plus M star of IN intersection E complement. Okay. Now you know that E is what is the assumption that we have?
E is measurable.
E
Is
is
measurable.
E is measurable. So and INs are also measurable. Intervals are measurable. Okay, that you can see. Outer measure and inner measure will be same for intervals. Now, and this intersection will be measurable. Somehow, I want to see that this is equal to summation N M star of IN. IN intersection E union E complement, and that will be M star of IN. Okay. So this part I will just use E is measurable. I know there is a gap here. Please think over. Okay. Because of the time constraint, I will leave it with a question mark. Give a thought. If we are not getting, you please tell me. Next time I will explain. Now, since INs are intervals, M star of IN will be equal to summation N length of IN. Do you agree?
Yes, sir.
For the time being, you this step, this jump you forget. Okay, this jump you forget. We will see. So you will get summation N length of IN. Thus, therefore, M star of A intersection E plus M star of A intersection E complement is less than or equal to summation N length of IN. But now you see the choice of IN. Summation length of IN is less than or equal to M star A plus epsilon. This is less than or equal to M star A plus epsilon by 1. Forget about that question mark. Think about it. And if you are not getting, we will revisit it in our tutorial. Okay, you have this. So, and this is true for any epsilon. Since epsilon greater than 0 is arbitrary, you get M star of A intersection E plus M star of A intersection E complement is less than or equal to M star of A. Okay. We used E is measurable. But for any set, the reverse inequality we have. Yes or no? See how I
Yes,
start.
sir.
This, not this. Yeah. This I have for any set. But we have M star of A. This is true for any pair of set. Okay. Is less than or equal to M star of A intersection E plus M star of A intersection E complement. So combine them, you get, therefore, M star of A is equal to M star of A intersection E plus M star of A intersection E complement for every A subset of AB. Okay. Thus, if E is measurable, then E has this property. E will turn out to be a good slicer. Okay. Combine them. Thus, we proved the following theorem. Thus, we proved the following theorem. Can you tell me the statement of the theorem that we proved? Yes. What did you prove?
A set contained in bounded interval is measurable if and only if
E,
the
very good. E subset of AB is measurable, meaning inner measure is equal to outer measure if and only if for every A subset of R, you can cut this A into two pieces using E, and if you find the measure of that two piece and add, you will get measure of the original. And that is true for any set. So this E is like a good slicer. It can cut any set into two pieces.
Sir, A belongs to AB होना चाहिए ना?
Yes. Sorry. Our world is AB. Because you want to connect outer measure, inner measure, etc. And inner measure is defined. I have defined only for bounded sets. Is that okay?
Yes.
Give me 2 minutes.
Yes, sir.
So far, so good.
Yes, sir.
Yes, sir.
Once it is measurable, then those sets will be good slicer, and those which are good slicer are going to be measurable sets. Okay, and this condition is called Carathéory splitting condition. You have to check the spelling. French mathematician, splitting condition. So the Lebesgue defined measurability like Riemann. Inner measure is equal to outer measure. That was the definition for Lebesgue. But Carathéory observed that is same as saying that a set measurable is same as saying that set is a good slicer. It can cut any set into two pieces so that there is no wastage. Measure of the whole is equal to sum of the measure of the two parts. Okay, this was Carathéory observation. Okay, so what is our development is that a set inside AB is measurable if and only if it satisfies Carathéory splitting condition. Is that okay?
Yes, sir.
Yes, sir.
Now, so this was Lebesgue idea of measurability. Inner measure is equal to outer measure. Carathéory came and told you that you can view it in a slightly different way, like cutting different sets. Because this is an if and only if statement, that is the last point that I want to make. Because this is an if and only if statement, this Carathéory splitting condition can be treated as definition of
Measurable set.
Measurable.
Measurability. And if you see, in order to have this category splitting condition, everything involves only outer measure. Yes or no?
Yes,
Yes.
sir.
And outer measure is
Yes.
defined for any set, subset of R, need not be inside AB.
Yes.
So, if a set satisfies category splitting condition, we call it as measurable. Okay, that is the definition. So that will be taken as the definition. So, definition. A subset E of R, now it is R, okay, is said to be Lebesgue measurable. Lebesgue measurable if for every A subset of R, M star of A is equal to M star of A intersection E plus M star of A intersection E complement. This is the definition of measurability. Is that clear?
Yes, sir.
Yes, sir.
This is
Yes, sir.
how any standard textbook will start. Immediately after talking about outer measure and so on, and proving that outer measure will not satisfy all the four conditions, the next thing would be this definition. But the question is, why one need this definition? How is it motivated and so on? Everything comes with like this. The idea is not only outer measure, you can also approach it via inner measure. And if inner measure is equal to outer measure, copying Raymond's idea, Lebesgue declared such things as measurable. Okay, and later Carathéodory came and told that measurability can be viewed in a different way using this. Okay, now onwards, that view will be taken as the definition. And advantage of that view is that it does not involve inner measure. It involves only outer measure. So that can be taken as definition of measurability for any subset of R. Is that okay?
Yes, sir.
So this
Yes,
is
sir.
now this is our starting point, and we will pick up from this definition next time. A subset is said to be Lebesgue measurable if that subset is a good. Always have this picture in mind, okay? Most of the student, when write Lebesgue measurability condition, it get confused and write M star E here. M star E equal to something. Because you are declaring E to be measurable. So naturally, you will feel that the condition is like M star of E equal to something. It is not. It is not. Okay. So that error you should not make. That's why I am saying A is like an arbitrary set. And the measurable set means it is like a slicer. It is like a good knife. This knife will cut A into two pieces. And these two pieces, if you add, you will get original. For what A? For what A?
For every A.
For every A. Okay. So this E is fixed. The cutter is fixed. You want the cutter to be measurable. Okay. Now you feed different A. Whatever A I am feeding, I can split into two. This is a very sharp slicer. So that you feed anything, it will get splitted and there is no wastage. There is no wastage in this splitting process. Okay. Are you with me?
Yeah, yes, sir.
So don't write E is measurable, Lebesgue measurable if M star of E equal to something. No. M star of any arbitrary set is equal to sum of the two parts. Okay. So with this, let me stop. And this is the point from which we are going to pick next time. But remember, our aim was from 2 power R we have to reduce it to m. Yes or no?
Yes, sir.
Yes, sir.
So that the Lebesgue countermeasure becomes countably additive. That was our aim. Now we have defined Lebesgue measurability. Now, natural question is how this definition will help us for reducing from 2 power r to m. Can you guess what may be that m?
E.
Just a guess.
All measurable, sir.
Collection of all measurable sets. That is going to be our m. Okay. Collection of all Lebesgue measurable set, if you take, that is going to be our m. And on that m, Lebesgue countermeasure is going to be
Countably additive.
Countably additive.
additive. So this set of all Lebesgue measurability is the m that we are searching for. Okay. Sorry, because I extended a bit. Otherwise, I have to repeat all these things. So next time I will start only from this definition. Okay. Let me stop recording and leave the meeting. Thank you.
Thank you, sir.